Okay, good morning. My name is Mr. B.N. Mopeti. I want to take you on a lesson on reflection and refraction of light. Now, the points to note: when an object is reflected in a plane mirror, its image is, number one, the same size as the object. Number two, the same distance behind the mirror as the object is in front of it. Number three, left, right, inverted. And then number four, virtual. So I want to explain each of these points one by one. But before I do that, I want you, when you get some free time, go and stand in front of a mirror and then raise your left hand. You'll find that your image will raise its right hand. If you have a scar on your left cheek, your image will have the same scar on the right cheek, okay? And then if you look at your reflection in the mirror, number one, your reflection is the same size as you, okay? So that means that the image is the same size as the object when it comes to reflection, okay? And then number two, your image is actually technically the same distance behind the mirror as you are in front of the mirror, okay? And then, like I said, if you have a scar on your left cheek, your image is going to have the same scar on its right cheek. So we say that the image is actually left-right inverted, okay, with reference to the object. And then lastly, the image is virtual. We say it's virtual in contrast to being real. We say it's virtual because light rays do not actually come from or go to the image, okay? They appear as though they are coming from the image. So we use the term virtual to show that these light rays do not come from the image, okay? Right, so it's important to remember all these points and to also understand what they mean. Now, we've got a diagram there. You can see this is the object, okay? Now, how do you draw the image of an object? First, you have to sketch two rays from the object up to the mirror. So we can see that we've got two rays there. There is ray number one, and then it has been reflected there. There is ray number two, it has been reflected. This is the mirror. This is the mirror. So I want you to take note of the law that states that the angle of incidence, this is the incident ray, okay? And then this is the reflected ray. This angle of incidence, which is drawn between the ray and the normal. The normal is just a line, okay? A line which is 90 degrees to the mirror. It's 90 degrees to the mirror. 90 degrees, okay, to the mirror, okay? So that's a normal there. This angle here, the angle of incidence, is equal to the angle of reflection. So if this is 45 degrees, it means that here is 45 degrees as well, okay? So we draw two rays, taking note of their angles of incidence and angles of reflection. You can actually measure this angle using a protractor, okay? And then you can generate this line by measuring the same angle here, okay? And then extending your line accordingly. So we draw two random lines. There's the second one here. We also have a normal there, which is 90 degrees to the plane of the mirror. And then its angle of incidence here should be equal to the angle of reflection there, okay? So after doing that, the observer will be here, okay? So if you extend these two lines, right, and then they pass through the mirror, here they'll be dotted because they are not actually coming going there or coming from there, okay? They're not coming from there, so we are drawing dotted lines. But if you extend them, there's a point where they are going to intersect. That point is the point where this image will be, okay? So if you look at this distance here between the image and the mirror, and the distance between the object and the mirror, this distance here is the same, okay? This distance is the same as this distance, right? So now, apparently, take note of the direction of the rays. The rays are generated there at the object, okay? So they go, then they strike the mirror, then they are reflected. So their direction is still coming down there, okay? Same as this one here. So apparently, we say that the image there is virtual because these rays are not coming from there, but they appear as though they are diverting from that point where the image is, okay? Right. So you need to be able to do this. You just draw two random rays, okay? Two random rays. Then you draw your normals at 90 degrees to the mirror. Then you measure this angle here, and then you reproduce that angle there. Since this angle is equal to that angle, then you extend that line coming down there, okay? You do the same here. You extend that line coming down there, right? Now, we have here a diagram which is showing how to draw an image I of an object O. So I was saying basically there are 4 steps which we have to know. So there is the object there, okay? The object is right there. So what do we do? Like I said, you're going to draw 2 lines, okay? And then you draw the normal there, which is 90 degrees to the plane of the mirror. Okay, that's step number 2 there. And then step number 3, you measure this angle here. Okay, you measure that angle as well. Then you reproduce the angle here, and then you draw your rays coming from there. These are the reflected rays. Now you draw your ray also coming from there, and then it's coming down here. So the observer there will be seeing as though these rays are coming from a certain point behind the mirror, which is that point there. Now that point is what we call the image. So you have to understand that the object is the real thing, okay? And then the image is the virtual thing. So you are an object. The image is what you see in the mirror. It's the reflection of you, okay? Right. Now, I've already covered these steps here. Like I say, step 1, draw your mirror line, etc., etc. So you can go through that if you want to make notes. Now, converging lens. Okay, we've got 2 types of lens in physics. We've got what we call converging lens, also known as convex lens. Then we've got diverging lens. So your syllabus covers converging lens only. Okay, so you have to know these converging lens, which are otherwise known as convex lens. Now, a lens is a shaped piece of transparent glass or plastic that reflects light. Yeah, it's usually made of glass, okay? Now, when light is refracted, it changes direction due to the change in density as it moves from air into glass or plastic. So basically we're saying that when light is refracted, remember we're now talking about refraction, not reflection. Now in refraction we have light which is moving from one medium to another. So now the medium from which the light is coming from and the medium to which the light is moving into, you have different densities. So this causes the light to change direction. That process whereby the light changes direction is referred to as refraction. Okay, we refer to that process as refraction. So when light is refracted, it changes direction due to the change in density as it moves from air into glass or plastic. Now lenses are used in cameras, telescopes, binoculars, microscopes, and corrective glasses. Now, corrective glasses are the glasses worn by people who have eye problems or problems with vision, okay? Now, a lens can be convex or concave. I'm repeating this point. So I said we are going to focus only on the convex lens, okay? We're going to focus only on convex lens. Now, your syllabus will only look at convex lenses, which are also known as converging lenses, because they make rays of light which pass through them to converge to one point, which is called the principal focus. Okay, so converging lenses, they'll bend light. Okay, they'll have parallel rays which will be bent, and then they'll be made to meet at a certain point, which we call the principal focus. Okay, right. So there are three green lines going from the top of the object through the convex lens and up to the top of the image. This is supposed to be lens, so please make that correction. Is convex lens. Okay, so we have three green lines. So basically, if you want to generate this image, if you're given this and these distances f and 2f, and this distance as well, f and 2f, and then you're given the object. So you're given the object, its position can be drawn on the exam paper. Then they ask you to sort of like indicate where the image is. Okay, so what's going to happen is that there are three lines which are there. There are three lines which are there, so you can use any two of those. Now these lines, the way they move, you should take note of the way they move. We've got this one here which moves straight, and then it bends when it reaches the convex lens. It'll bend and travel through this F point here. Okay, it'll travel through that point there and then come down. Okay, then we've got the second line, this one here, which travels through what we call the optical center. This one goes straight. It is not refracted. Okay, then we've got the third line, this one, which travels through F. Okay, on the other side, it travels through F on the other side, unlike this one which travels through F on the opposite side. Okay, this one travels through F on the other side, and then straight when it strikes the convex lens, it goes straight. Okay, so we've got the three lines. Let's see their movement. Straight, bending through F. Okay, going through F, then bending and going straight. Okay, and then we've got this one that just goes straight. This one is not refracted. So you just need to have two of these lines in order to draw the top of the image. If you use this one, which travels through F and comes down there, and you use this one here, the point at which they intersect will give you F, isn't it? So you can use either two of those three. If you want, you can use all three, but you basically need two of them to generate the top of the image. Then you draw down, then you touch this line here, then you'll get your image. So apparently, you can see that if F is at such a position, okay, you don't have to claim this. If F is at such a position, then you draw a straight line which will bend through F, and then you draw this one here which goes straight. You'll find that the image produced by the object, which is at this position, is actually small. It's smaller than the object. Okay, now let's go through the notes. Only a minimum of two of these three lines need to be drawn to get the top of the image. In this case, the image is real. Okay, it's real as opposed to virtual, which was the case with the mirror image of an individual. It's real because we actually have rays, light rays, which actually go to the image. And then it's upside down, it's inverted, as you can see. It's upside down as compared to that position, which is right side up. Okay, and then what else can we say? It's diminished, right? The image is smaller than the object. Now you need to remember the meanings of these terms and also how each of the three lines moves from the object to the image, right? And then you also need to note the F's in the diagram above. Each is known as a principal focus. So each of these F's here is known as a principal focus. This is 2 times the length of 2 times the focal length. Okay, there's the focal length, the length from the optical center to the principal focus. This is the optical center here. Okay, right. So you need to remember that, right? Okay, so there are some terms which you need to take note of. We've got this here. This is the optical center. This is known as the principal focus. This is 2 times the principal focus. It's 2 times this length here. Okay, 2 times that length. So it's known as 2 times the principal focus. And then we've got this line here. This line here, which is dotted, is known as the principal axis. Okay. Right, and then we've got this distance. This is known as the optical center. The distance between the optical center and the principal focus is known as the focal length. So you need to remember these terms. Right, and then so we've got 3 rules which we need to take note of. We don't have to remember the terminology, but we just have to remember what the rules say about the movement of light rays. So we've got 3 rules. So we can have light which travels this way. It will travel like that, parallel to the principal axis. It will travel this way, and then when it strikes the convex lens, okay, when it strikes the convex lens, it will bend, it will be refracted, and it will pass through the principal focus on the other side of the lens, okay? The principal focus on the other side. Remember, we've got 2 principal foci on each side, and then we've got 2 times the principal foci on each side as well, because light can either come from this direction and then be refracted this way, or it can come from that direction and be refracted this way, okay? Right. So rule 1 is saying that we have this ray of light which will travel parallel to the principal axis, and then it will be refracted after passing through the convex lens, and then it will pass through the principal focus. Okay, that's rule number 1. Now rule number 2, we've got this light that passes through the optical center. It passes through the optical center. This one emerges without any deviation. That is, it's not refracted at all. And then we've got rule 3. We've got this light here, this ray of light, which passes through the principal focus. And then after going through the convex lens, it will then travel parallel to the principal axis. Remember, this is the principal axis. The ray will then travel parallel to the principal axis after passing through the convex lens, after it has been refracted. Okay, so we've got those 3 rules. You only need to know 2 of them in order to be able to calculate or like in order to detect the height of your image. Okay, now we've got this diagram here. Okay, this diagram is showing that a convex lens has the ability to bend light rays such that they all converge. Now, to converge means to meet, such that all these light rays will meet at a certain point. Okay, this certain point here is known as the focal point. Okay, we've written it as F there. It's known as the focal point, right? Right. Now, focal points, it's important to note that there are 2 focal points. You may name them F1 and F2 if you wish. The focal points are equidistant from the lens, okay? They are the same distance from the lens, the same distance from the optical center. And then twice that distance from the lens gives you 2 times the focal length, i.e. 2f. So if you look at this diagram, you can see there that F2, and then you can see that F1 there, okay? And then you can see 2 times F2 on this side and 2 times F1 on this side. Okay, so the F and 2F points on both sides of the lens can be seen in this diagram, okay? Now, O is the optical center. Like I said before, O is the optical center. The distance between O and F2, O and F1 is known as the focal length. Focal length. This distance here is known as the focal length. Okay? Now, object and image. The size of the image formed depends on the position of the object relative to F and 2F points on the line. We're going to see this in the following slides. Now you can draw 2 of any of the 3 rays, isn't any of the 3 rays, you can just draw 2 of them and use them to determine the characteristics of the image which will be formed. Now, some of the possibilities you can expect are as shown in the following slides. So let's suppose the individual is beyond 2F. You don't have to claim this, okay? You can draw 2 ray lines any one of those three, isn't? So in this case, we drew this one, and then it passes through the principal focus on the other side, and then we drew this one, which goes through the optical center and is not refracted. And then the point where they intersect will give us the top of the image. And then we draw the image accordingly, touching the principal axis. This is the principal axis. Okay, so now just by looking at the image relative to the object, you can tell that the image is smaller than the object. You can also see that the image is upside down. Okay, so and then you can also see that the rays are actually passing through the image. So we're going to say that since the rays pass through that image, the image is real. And then, as you can see, the image is upside down, so we're saying that it's inverted. And then lastly, the image is smaller than the object, so we say that the image is diminished. So we've got real because these light rays actually pass through. Okay, they are passing through that image. Inverted because it's upside down. Diminished because it's smaller than the object. Okay. Right, so all you need to do is to be able to draw these here. You can be given this and everything else other than the rays and the image. So you have to come up with these rays and then draw the image. Okay, right. So there is case number 2. Apparently case number 2, if the object is on that position there, which is 2 times the focal length, you'll find that the image which will be produced will also be at that distance 2f, isn't? Or 2f2 rather, as shown in this diagram. Now, if you look at the image and the object which is produced in this case, using either 2 of the 3 ray rules, okay, you'll find that this image is the same as the object height, okay, is the same size as the object, right? That's number 1. And then number 2, it's real because these light rays actually pass through that image. And then it's inverted. Like I said before, inverted means upside down. It's inverted. It's not right side up like our object, okay? Right. There's another situation there, case number 3. If we place the image in between F1 and 2F1 there, and then we use either 2 of the 3 ray rules, and then we note the point where they intersect, we'll find that the image the image which is produced is larger than the object. Okay, it's larger than the object, so we say that it is magnified. And then that image is upside down, so we say it is inverted. And then lastly, that image is real because these light rays actually pass through that image. Remember the situation of the image produced in reflection. The light rays didn't pass through, so we said the image that is produced, your mirror image is virtual, it's not real. Okay, but in this case here, the rays are actually passing through, they are not dotted lines, so we're saying that that image is real. There's another case there, case number 4, right? If we draw our object on F1 and then we use 3 of the 2 of either of those 3 ray rules, we'll find that these rays will not intersect at any point, isn't? And they'll continue that way, traveling parallel to each other up to infinity. Okay, so what happens, we say that but you don't expect to find such a scenario in O level, so this is just there for appreciation, right? So this will have a highly magnified image being produced from the object, and then that image will be real and inverted. Okay, it will be real and inverted. Right. Now we want to look at case number 5. Now case number 5 is very important. Case number 5 shows how a magnifying glass works or operates. Okay, so in case number 5, this one here is our image, and then this is our object. So first, before we go to the in fact, this is our object and this is our image. Okay, point of correction, this is our object and this is our image. So let's start with the object first. We're going to use 2 of the 3 ray rules. There is the first one, passing through F2 there. There's the other one there, passing through the optical center. Now these ones are actually diverting. Okay, so we're going to trace them back, right, to a point where they meet, which is this point here. And then from that point, we're going to draw the the image. So you can see that the image, as compared to the object, the image is virtual, okay? Because these lines are dotted, right? They are dotted. The light rays are not actually coming from that point. They appear to be coming from that point, but they're actually not coming from that point. So we're going to use virtual, okay? And then we're saying it's erect. In this case, it's not inverted. It's erect. It's right side up. It's right side up in the same way as the object. So we say it's erect. And then it's magnified, right? It's magnified as opposed to being diminished, because this image is larger than the object, okay? Right. So that's something that you need to take note of. Right. That brings us to the end of my presentation. Good day.